Greetings, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to continue our discussion of the Pythagorean Theorem, but we are most likely going to be looking at it in a way that you have never looked at it before. So let's get started. Our objective for the day: the student will learn to use the converse of the Pythagorean Theorem in order to classify unknown triangles. I'm not entirely sure of when this lesson will be coming into play, but I believe it will be the Wednesday following spring break. You can leave the date blank and fill it in later on. As always, press pause anytime you need more time to complete your notes, and then press play when you're ready to move on. So let's take a look. Okay. First off, a little basic review from once upon a time. You do not necessarily have to write this down. Okay, but let's discuss anyway. What did a converse do? Okay, hopefully you can remember from back in the day when we were talking about our conditional statements, if P, then Q, where P was our hypothesis and Q was our conclusion. A converse took the hypothesis and the conclusion, and it reversed the positioning of the information. Okay, so it switched the hypothesis and the conclusion of the conditional statement. Now, some of you never did really get a grasp of this. That doesn't mean just to take the if and the then and switch them. It means to reposition the material so that the reverse of the statement is actually being made. So Pythagorean said, if your figure is a right triangle, then a squared plus b squared equals c squared. So the figure being the right triangle was the observable piece of information. And if you could observe that, then we established that a leg squared plus the other leg squared did in fact equal the hypotenuse squared. Okay. So in summary, using the fact that you had a right triangle, basically put us in a position to find a missing side length. Okay, if you have stopped taking notes, you need to get back to taking notes, because here comes your new information. The converse of this theorem is going to be true as well. And we stated this was going to be the case with the strongest of the mathematical theorems that we worked with this year, that not only the rule would be true, but the converse would be true as well. So the converse is going to say, okay, if you can prove that a squared plus b squared does in fact equal c squared, then that means that your figure is a right triangle. Now that may not be all that exciting by itself, but we're going to be using it in a way that you probably do not anticipate here in a moment. Okay, so in summary, the converse is going to allow us to use the side lengths of an unclassified or unidentified triangle to tell us if it is a right triangle. So in the past, you have never been allowed to use the Pythagorean theorem unless you were confident that you did have a right triangle. Now we will not know if we have a right triangle, but Pythagorean is still going to help us out. Okay, so let's take a look. We have a triangle, and we are questioned as to whether the triangle is a right triangle. Now, I know what some of you are already thinking, and I hope that you will be able to overcome it, because some people are going to look at it and go, nope, it's not a right triangle, because I can look at it and I can see it's not a right triangle. Okay, well, that's just not nearly good enough in geometry. It does not matter what the picture looks like. It matters what the math says. Okay, so let's have a look at the math. Now, by the converse of the Pythagorean theorem, if a squared plus b squared does actually equal c squared, then we do have a right triangle. Okay, well, just like with regular Pythagorean theorem, we had better get the right information in for the hypotenuse. So we still need to identify the hypotenuse correctly, even though there's no right angle marked. But as we discussed yesterday, okay, we know that the hypotenuse is always across from the right angle, so that means that the hypotenuse is going to be the largest side of the triangle, because the potential right angle should be the largest angle of the triangle. Okay, so that means our 25 is going to be our hypotenuse. 7 and 24 would be the potential legs of the triangle. And I put a question mark above the equal sign because we do not know. That is actually the question. Is the left side of this actually equal to the right side or not? Well, let's simplify the math and figure it out. 7 squared is hopefully a value that we know, that is 49. 24 squared is probably a value we do not have memorized, so we would probably be going to our calculator to help us know that 24 times 24 is 576. Probably the same on the right side, 25 times 25. We would probably be going to our calculator to find out that that is 625. Okay, so 479 plus 576 on the left. That needs to be combined. Those are definitely like terms. 49 plus 576, hopefully you can see, is 625. Okay, so what we're staring at is a statement that says 625 is equal to 625. Obviously, that is correct. So what does that mean? It means that a squared plus b squared did in fact equal c squared, and when that happens, the converse of the theorem says, yep, that is a right triangle. Now, obviously, we are talking about a question that could be answered with the flip of a coin, heads being yes, tails being no, that kind of thing. So clearly, this would be a question that even if you get it right or wrong, you're not going to get any credit without the math to support your yes or no answer. Let's look at another one. Okay. As we've already seen, sometimes with the right triangles, especially where Pythagorean theorem might be involved, we are going to see side lengths that are going to be in terms of radicals. So here we have an example that does have some radical side lengths. Okay, question remains, is this triangle a right triangle? Well, we got a little bit of a different issue on this particular triangle. Okay, we keep being told that we need to make sure we get the hypotenuse in the right position. And we're also told that the hypotenuse is going to be the longest side length of the triangle. The question is, which side length is the longest side length? So if you cannot determine which side is longest by observing the values, then here is an instance where you may use your calculator to help you decide which side is longest. However, that is the only part you can use your calculator for. Okay, you will go back to using the radicals when it comes time to plug into the theorem. So let's observe our three side lengths. Okay, obviously the 6 is a 6, but 4 root 2 is approximately equal to 5.66, and that is rounded off, and 5 root 3 is approximately equal to 8.66. So clearly the largest side length, the hypotenuse, is 5 square root of 3. So when we plug into our theorem, we will make sure that we get 5 square root of 3 plugged in as c, the hypotenuse. Okay, so plugging into our theorem, here's the numbers that we are looking at. Okay, well, this is a little bit different math than some of us have seen. Okay, we have 4 square root of 2, which needs to be squared. Then we have plus 6 squared. Well, 6 squared is easy enough. And then on the right side, we have 5 square root of 3 squared. So some people are probably wondering, how does the square affect these radicals? Like on the first term, does the 4 just go get the square? Does it just go get the 4? Or does the square go underneath the radical and get the 2? Does it go and get both of them? Exactly how does it work? And the answer is the square distributes, and it actually goes and gets both of them. Okay, so we've got 4 squared times the square root of 2 squared plus 6 squared. And does that equal 5 squared times the square root of 3 squared? Now, cleaning up the numbers here, of course, we've got 16 square root of 4 plus 36. Is that equal to 25 times the square root of 9? Now, these radicals are obviously not simplified. Hopefully, you don't have to go to much math to figure out that the square root of 4 is 2. So that first term is going to be 16 times 2. And the term on the right is going to be 25 times the square root of 9, which is 3. Okay, so there they are, 16 times 2. And on the right, 25 times 3. Well, 16 times 2 is 32. 25 times 3 is 75. So now what we have is 32 plus 36, and the question is, does that equal 75? And it does not. 68 does not equal 75. Okay, so what did we just determine on that? Okay, we tried to plug these values into Pythagorean theorem. A squared plus b squared did not equal c squared. So by the converse, this is not a right triangle. And again, just writing down the word no without any work on there, that is the correct answer, and it will get you no credit. Make sure you show your work if you want your credit. Okay, now the information that's going on here is actually telling you something else. So the converse of the theorem, it is capable of announcing to us whether we have a right triangle or not. Okay, but if it announces to us that if it is not a right triangle, then we can actually determine whether the triangle is acute or obtuse. Okay, so by the converse of the Pythagorean theorem, if a squared plus b squared does equal c squared, then we have a right triangle. But what if a squared plus b squared does not equal c squared, like we just saw? Okay, well, here's what happens. Okay, so as I said, there's more information here than what we have been looking at so far. Okay. And by the converse of the Pythagorean theorem, if you plug in your values like we have been plugging them in, and you come up with information that says a squared plus b squared is greater than c squared. So the sum of the legs being squared is actually more than the hypotenuse being squared, then that is not a right triangle. That one is actually an acute triangle. Okay, and very similarly, by the converse of the Pythagorean theorem, if your legs being squared, the sum of them, is smaller than the hypotenuse being squared, that one is not right either. That one is going to be obtuse. Okay. And one of the easier ways to think about this converse is actually to think about that equal sign that should be in there in the Pythagorean theorem. Okay, remember the equal sign acts like a scale, like a balance for the equation. And when the equation tips one direction or the other direction, that is going to mean something. And I'll try to explain that a little better when we cover the notes in class together. Okay, so copy the converses down for now. I'll explain it more in class, and let's look at an example. Okay, the last example we looked at, we tested to see if a squared plus b squared did equal c squared, and it did not. We ended up with a statement that said 68 was trying to be equal to 75. That is obviously a false statement. Okay, so the converse of the theorem not only wants us to know that this was not a right triangle, it also wants us to know, is it acute or is it obtuse based upon which side of this equation is larger. Now, very clearly, 68 is smaller than 75. So the sum of the legs being squared was smaller than the hypotenuse being squared. Okay, and which direction did that mean? Did that make it acute or make it obtuse? Well, by the converse of the theorem, if the hypotenuse was larger, okay, than the legs being squared, then that triangle was an obtuse triangle. Okay, so this is going to put us in a position where we can not just decide right triangle, yes or no, but what kind of triangle, acute or right or obtuse. Okay, so let's look at one more real quick together. Classify the following triangle as acute or right or obtuse. I apologize if you can hear my daughter in the background. She's watching TV and something is obviously found very funny with her and she is belly laughing in the next room. But anyway, okay, we have a triangle here. Okay, we have a 4, 5, 6 triangle. Do not call it acute because it looks like the angles are acute. If it is acute, it'll have to be for a mathematical reason, not an appearance reason. Okay, so let's see what we can do. Now, obviously, the hypotenuse is going to be 6 in this case. So we have a 4 squared plus a 5 squared. And the question is, does that equal 6 squared? If it does, good, it's right. If it does not, then we'll evaluate which direction it is tipped, and that'll tell us what kind of a triangle it is. Now, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Okay, and on the left side, 16 plus 25 is 41. 41 is obviously not equal to 36. Okay, so it's not a right triangle. The legs being squared are larger. Okay, so 41 is larger than 36. The legs being squared, the sum of the legs being squared is bigger than the hypotenuse being squared. So what kind of a triangle does that actually make it? That one makes it acute. Sorry, I keep hitting the bottom bar and pop-ups keep, the little preview windows keep popping up on the screen. Okay, one final example. I'm going to leave this one to you to give it a try. I want to see this worked out in your notes when these notes are due in class, and then we will cover this example together to make sure that you do understand it and that you did get it right. Okay, but we have a 5, 7, 9 triangle, and we are asked to classify the triangle as being acute or right or obtuse. Give this one a try. I appreciate you finding time to do your notes. We'll see you in class one of these days soon.